Now students, let's move on to the fifth question, which says a body of mass m slides down an inclined surface which ends into a vertical loop of radius r is equals to 40 centimeters. What must be the height h of the inclined surface for body not to fall at uppermost point? Now students, he is asked us to find the height h with which the inclined surface should be aligned so that the when the body approaches the upper point of the inclined surface, it should not go out and fall during the uppermost point. Now Lakshman shows how to solve this problem.
Yeah, Krishna. Actually, in this sort of problems, what we actually should get to know is when the body is at the uppermost point, the normal body will be having the normal reaction force and the gravitational force. The forces,
Okay.
we'll just see the forces acting on the body at the uppermost point of this loop. So what we'll be having is the normal reaction, which is acting downwards, and also the gravitational force acting downwards, and the centripetal force which is acting downwards, that is equal radially inwards, not downwards, that is
Okay.
equal to mv square by r. So what initially is like n plus we are just equating the forces at the highest point. N
Okay.
plus mg is equal to mv square by r. So at the limiting position, at the limiting point where the body can reach the uppermost point, n should be greater than or equal to 0. So
Okay.
here it is just have to reach the uppermost point and will not fall. So we can take this as the limiting case, that is n is equal to 0. So
Can
in
you
that
just please
case,
tell us why the normal force should be greater than or equals to 0?
in order body not to get detached from the loop, the
Okay.
n should be greater than or equal to 0.
Okay.
In this situation, we will be getting mg is equal to mv square by r, and thus v square is equal to gr. Let
Okay.
us name this as the equation. So now initially the body is at height h, so the initial potential energy of the body will be equal to initial potential energy of the body is equal to mg capital H, as it is at the height h, and the final potential energy of the body will be equal to mg into here we can see the height of the body at the final position is 2r, as this is the radius. It's twice it's the diameter, that is twice the radius. So final height is 2r, mg into 2r, and as the final kinetic energy will be equal to half mv square.
Okay.
And the body is initially left from the height h, so the initial kinetic energy will be equal to 0 according to law of conservation of energy.
Okay.
Law of conservation of energy, energies can be equated. So PEI plus KEI is equal to PEF plus KEF. So this will be equal to mg capital H plus 0 is equal to mg into 2r plus half mv square.
Okay.
So after solving this, we will be getting H is equal to 5 by 2r, that is 2.5 r.
Now, how he has solved this question, he has started by drawing the free body diagram of the body when it reaches the uppermost point, where the normal reaction will be acting downwards and the mass of the body will be acting downwards and the centripetal force will be acting downwards, and he has written the free body equation and he has solved the question. And when the mass is rotating in the inclined plane, if it has to not leave on the uppermost position, then it should have some contact force with the inclined plane. If it has to have any contact force, it should be greater than or equals to 0. But in the question, it was asked to find out
How the body
how the body should not fall at the uppermost point. So that's why we have considered n should be equals to 0 because it's the uppermost point. And then he has equated the initial kinetic energy plus potential energy and final kinetic energy plus
Potential energy.
potential energy by using law of conservation of energy, and solve the question.
So we've come to problem 6, and it is a passage type question. It says a small block of mass 1 kg is released from rest at the top of a rough track. The track is circular and the arc is of radius 40 meters. The block slides along the track without toppling, and frictional force acts on it in direction opposite to instantaneous velocity. Work done in overcoming friction up to point Q is given to be 150 joules. And we are asked to find the speed of block when it reaches the point Q, and also the magnitude of normal reaction that acts on block at point Q. Okay, so how do we start with this?
Yeah, basically this is a passage type of questions. The
Right.
passage type of questions,
Mhm.
we need to just find the logic how to do the question.
Okay.
Let us go to the question A.
Okay.
Initially the block is at point A and it has moved to the point Q.
Right.
So at the point A it is having velocity 0, and let us assume at point Q velocity B is equal to V.
Okay.
So in this sort of questions, the actually it is given work done in overcoming the friction is 150 joule.
Right.
We know friction is a non-conservative force.
Mhm.
So work done by the non-conservative force in this case is equal to 150 joule.
Right.
So we know according to work energy theorem,
Mhm.
according to work energy theorem, we know work done by the conservative plus non-conservative forces
Right.
is equal to negative of change in mechanical energy.
Correct.
In the given situation, actually there is no conservative forces.
Right.
So work done by the non-conservative force, that is friction, is equal to negative of change in mechanical energy. Now let us deal with the mechanical energies of the system.
Right. Actually,
at point.
what about gravity? Gravity is there, and it is a conservative force.
Yeah, gravity is a conservative force, but work done by this conservative force in getting down will be equal to 0, because at both positions A and B,
Okay.
conservative forces acting on, that is gravitational force acting on the body, will be equal. So there will be no conservative work
Okay.
done.
So right. So because the initial and the final states are same, so
Yes,
work done by conservative
yes.
force will be 0. Right.
Let us go to the mechanical energies.
Mhm.
At position A, it is having 0 velocity, so kinetic energy initial will be equal to 0, and the potential energy initial will be equal to mgh. Actually in this case, h is equal to the radius of the circular track.
Right.
So
It is also equal to R.
Yes, it
Correct.
is. So it is equal to mgr.
Right.
Let us go to position B.
Mhm.
In position B, we assume the velocity is v at position Q.
Right.
So actually this is position Q. So the kinetic energy final is equal to half mv square, and the potential energy is equal to mgh. Let us find the height of Q from the top.
Right.
As this is a triangle, let us name this point as L. In
Okay.
triangle QLP,
Right.
we are getting cos 60 degrees is equal to P. Yeah. Take another point as S.
Right.
No, so now cos 60 is equal to PS by PQ.
Okay.
That will be, PS will be equal to R by 2.
Right.
So LQ will be is equal to R by 2.
Yep.
So the potential energy, final potential energy is equal to mg R by 2.
Right.
So now we take the change in mechanical energies, that is equal to final energy minus initial energies.
Correct.
That is equal to change in mechanical energies is equal to mg R by 2 plus half mv square. This is final energy
Right.
minus initial energy.
Okay.
This will be equal to half mv square minus mgr by 2.
Right.
As we know, as we discussed about, work done by the non-conservative force is equal to negative change of mechanical
Exactly.
energy.
So this will be equal to minus 150.
Yes, this will be equal to minus 150. So we will be getting minus 150 is equal to minus mgr by 2 plus half mv square.
Okay.
So by solving this, we will be getting, as we know, r is equal to 40 meters and g is 10 meter per second square,
Right.
and given mass is equal to 1 kg. So we will be getting v square is equal to 100,
Right.
and that is equal to v is equal to 10 meter per second.
Correct.
Yeah. So in the given question, we need to find the velocity of block at point Q.
Correct.
By work energy theorem, we got velocity at point Q is equal to 10 meter per second.
Right.
Now let us go to the question B.
Okay. So here
Uh,
we have to find the magnitude of normal reaction that acts on the block at point Q.
Yeah, for this, when we get like this sort of questions, what we do is draw a free body diagram. Let
Right.
us change the color.
Okay.
We draw the free body diagram of the block at
Mhm.
position Q.
Right.
At this position, the normal reaction of the block will be perpendicular to the instantaneous velocity, as the instantaneous velocity is in this direction. So the normal reaction is perpendicular to the instantaneous velocity, and it is inward.
Right.
Because it is away from, as we are considering the block, it will be upwards.
Exactly.
For the block.
Hmm.
So in this case, the gravitational force acting on the body mg is
Mhm.
acting downwards,
Right.
and we know this is 30 degrees as
Okay.
given. So in the opposite of the radially outward direction, this
Mhm.
will be equal to mg sin theta.
Right.
So from this, just we are drawing the net force equations.
Mhm.
F net.
So is there actually any application of the work energy theorem in this part?
No, in the second part, just we are doing by the force methods.
Right.
So actually, the other force acting is centripetal force, which will be acting radially inwards. That is
Mhm.
equal to mv square by r.
Right.
That is the F net. So F net is equal to mv square by r.
Okay.
And just by considering the normal reaction and the gravitational force, we will be getting F net is equal to n minus mg sin theta.
Mhm.
Here in this case, theta is 30 degrees.
Right.
So that is equal to n minus mg sin 30 degrees. So F net is equal to mv square by r.
Right. So the
As
thing
we
to
got
note
from-
here is, mv square by r is never another force. It is just equal to, the net
Yes,
centripetal
yes.
or the centrifugal
Yes.
force. Right.
In the above question, we actually got v is equal to 10 meter per second,
Right.
and we know r is equal to 40 meters.
Okay.
So by just equating this, we will be getting n is equal to 100 by 40 plus 10 by 2. That
Okay.
is equal to 7.5 Newton.
Right.
Yeah.
So that gives us the normal reaction at point Q.
Yes.
Okay, so I'll just summarize the question for you. We are given the system in which a block is sliding down this curve, and we're given that, this angle here is 30 degrees. So first we were asked to find the speed of the block. So we applied the work energy theorem, in which says that, the work done is equal to the negative of the change in mechanical energy. So we proceeded to find the potential and the kinetic energies at 2 points, and we could equate that to minus 150 joules, which was already given to be the amount of work done. So from there we got the expression for velocity, and it came out to be 10 meters per second. In the second equation, in the second part, we didn't have to apply the work energy theorem at all. We were just supposed to write the force equation. And since we had found out the values for v, it was not difficult for us to get an expression to get the value of n. So an interesting thing to note here is that, for example, the gravity is a conservative force, but we can see that the work done, the total, the state, in those terms will be the same at both positions. So we don't need to really consider that when we are talking about the work done. So yeah, this was problem 6. And we'll move on to the next one now. So in problem 7 we have an expression for potential energy in terms as a function of r, and we are given it to be a by r square minus b by r, where r is the distance from the center of the force and a, b are positive constants. So the the things to note here is the expression itself and the fact that r is measured from the center of the force and that a and b are both positive. So we have to find the equilibrium distance and we have to find the work done to move the particle from equilibrium to the infinity, in fact. So obviously, so what exactly is the equilibrium distance? What is the characteristic which defines equilibrium distance?
Yeah, what exactly is like in the given question we got the UR.
Right.
In the given question
Right.
we got UR. What UR is considered as the potential energy here.
Right.
UR is equal to A by R square minus B by R.
Okay.
You know, when UR is given the potential, that is when potential energy function exists, the force is a conservative force.
Right.
So work done by the conservative force is equal to F into dr.
I'll just reiterate that the potential energy is only defined for a conservative force. So the
Yes.
fact that it exists means it's conservative, right?
Yes, and according to work energy theorem, this will be equal to negative change in the potential energy. As
Right.
it is not mentioned about the kinetic energy, we just take the potential energy here.
Okay.
Yeah. So F dot dr is equal to minus du.
Right.
F is equal to minus du by dr.
Correct.
As we have u as a function of r is equal to a by r square minus b by r.
Right.
We just differentiate it with respect to r.
Okay. Right.
So here we will be getting, this will be equal to minus 2a by r cube
Right.
plus b by r square.
Okay. So we've differentiated
Yeah,
with
just we have
respect to r.
differentiated
Right.
it. As we know, at the equilibrium position, the F net will be equal to 0.
Right. So I can already see that we will
F
get
net
r
will
to
equal
be
0.
2a
So
by b.
as du by dr is equal to F,
Okay.
du by dr is equal to minus F, and F net is equal to 0. We
Right.
just equate this term is
To
equal
0.
to 0.
Correct.
So this will be equal to 2a by r cube is
Uh-huh.
equal to b by r square.
Right.
In this way, we will be getting r is equal to 2a by b.
Correct.
So at the equilibrium, actually he asked the equilibrium distance. At equilibrium distance, the F net will be equal to 0, and we
Right.
got r is equal to 2a by r.
Okay.
Let us move to the part B of the question. They asked the work done to move the particle from equilibrium to infinity.
Right.
At the equilibrium, r is equal to 2a by b. So work done from equilibrium to infinity will be equal to change in potential energy from the
Infinity to this
infinity
point.
to
Right.
equilibrium. To
Right.
equilibrium.
Okay.
So this will be equal to at infinity, as u is a function of r.
Yeah.
If
Exactly,
we keep r
just
is
make-
equal to infinity,
Right. Since r is in the denominator, it will obviously
it
tend
will
to
be
0.
equal to 0.
Right.
U infinity will be equal to 0, and
Correct.
u equilibrium will be just equating this term in the r.
Right.
So we will be getting 0 minus a by 2a by b whole square minus b by 2a by b.
Right. So we get the
After
expression to
equating
be.
just, yeah, after just equating this, we will be getting minus b square by 4a
Mhm.
plus b square by 2a.
Right.
This will be equal to b square by 4a.
Right.
So work done to move the particle from equilibrium to infinity will be equal to b square by 4a,
Correct.
adjusting to the units.
Right. So this is the solution for the second part. So to summarize the problem, we were given an expression for the potential and potential energy, in fact, in terms of A and B2 constants and the distance from the center of the force. And we were asked to find the equilibrium distance, in which case all we did was equate the net force to 0, and obviously net force is equal to minus du by dr. And after that we were asked to find the work done to move particles from equilibrium to infinity, which was not a very difficult task if you had already found the equilibrium distance. All you had to do was subtract the potential energy at infinity In fact, you have to subtract the potential energy at this point from the potential energy at infinity, so we got the answer to be b square by 4a. So this was problem 7, and we'll move on to the next one now.